So problems keep happening with my videos. So I just realized that my last video, the video series session number 5, I think, was or 6, I can't remember. But um, apparently there was no audio. The mic wasn't properly plugged in, and I did not notice that. Anyways, um, let's keep going. That shouldn't stop us and that shouldn't delay us. So we've done a quick recap yesterday on the main concepts that we have covered, and as for today, we will be going through a couple more. Uh, so we've witnessed we found a quick summary um, on the main concepts that we might be interested in, and it's this one. It was a really decent summary. We didn't have to write things down and nothing of that sort, but I forgot to copy this to the drive, so let me do that right now. The reason I'm copying to the drive is that later I will have to cleanse things out and, um, next set. Yeah, this was a topic we were introduced to the last time, which is an index set is a set whose members label is basically elements of another set. Okay. Now, something that was a bit of confusing, there was a bit of confusion there on, um, when we were following the book, there were some weird terminologies used, and I really didn't think it needed to go this far. I mean, it could have been simply explained some other way, but let's like in this one, like you have S1, S2. These are different sets, and this is a collection of sets. Um, Collection of sets is basically called family of sets. For simplicity, we write this collection as S to I, where I belongs to the integers. So to integers. Now, in this case, um, the I is called an index set because it is the set. The elements of this set is what's used to label the collection of sets here. um, and in this case, the set I is indicated to be positive integers. So we have 1, 2, 3, 4, 5, 6, and so on to infinity. So the elements of this set are used to label the collection of sets here. And the positive integers in this case are called the index set. The union of the collection Si, so the union of all of these sets. As you can see, the union of all of these the union of all these sets, which is indicated by this symbol here, U. I belongs to the positive integers. Union, so it could be with Si, so it could be Si S1 union S2 union S5 union S20 for its worth. So the collection of Si is the set of all elements that are members of at least one of the Si. So it's a collection of all the elements of any one set. So if you go like, I know it's a bit weird um, using going through the terminologies when you're studying mathematics, but unfortunately we really have to really get a quick grasp on this because it will, as we will be going through different researches and different exercises and different sources out there, we will have to at least feel acquainted with the terminologies, or at least we'll be familiar with them. In this case, the union of the collection of the elements, which is denoted by the word symbols here, the union of I, as long as I is part of the positive integers, of Si, then of at least one Si. So the set of all elements that are members of at least one SI. So in this case, if you have SI, say you have S1, S1 union with S1, then it's at least the all elements in S1. But if you have S1 and S2, and you could go like this is what I mean. So if say S1 is the set of elements 1, 2, and 3, yeah? And then S2, now S2 is what's important because 1 and 2, these two labels here, these two labels belong to the positive integer sets. Now S2 could be, say, I don't know, 8, 7, and 6, something like that. So assuming you're saying assuming we only have S1 for now, so the union of S1, then according to the definition, should be all of the elements of at least one of the SI. So in this case, S1 union S1 would yield 1, 2, and 3. So the union would result to at least the element of one of the sets within the collection. Now if you go to S1 and S2, now if you merge these two together, then the union is basically 1, 2, 3, 8, 7, 6. Then, so the elements contain at least all of the members, at least, so it didn't say at most, but at least all the elements of one of the collection. So it's basically a logical explanation here. Since the index set is usually understood, we will simply write this as union SI. So in this case, the union is basically telling you the elements of the positive integers, the index set. In other words, we write US equals X. X belongs to SI for at least one I belongs to the positive numbers. So in this case, X belongs to SI, where I is one of the positive integers. In this case, it is the 1. Awesome. And that's what this definition is all about. Basically, that's my understanding. So this is out of the way. We should keep going then. And just for me to double check that the voice is being recorded, I'm just gonna pull out this. It doesn't look like there is an indication. Anyways, let's hope that it's recording. I've checked the plugs before I begin, so hopefully things are alright for now. So further with our topics here. The set of all x such that x is an element of Si for at least one I in the positive integers. Similarly, the intersection. Now the intersection is a bit different. Now going with our previous example, say we have S1 and then it is, let's just undo. So in this case the union would yield this. Now the intersection though, the intersection would yield 1, 2, 3, right? But the intersection of both these elements would yield an empty set, like the intersection of S1 and S1. So S1, S1, be it union, or intersection, or union C. Okay, so in both cases it's the same, but in the intersection things are a bit different. So when you intersect both the same element itself, then you will have the same. You'll have at most one. But assuming there are the same elements, then there is no way we will get at least all of the elements. So it could be any of the elements. The intersection could be any of the elements and not at least all of the elements of one of the one of these sets. In the intersection, it could be any or none. Let's see if this is correct. The intersection is given. So x belongs to Si for all I belongs to the positive integers. For example, if s t if s okay if s is t intersection with x, then s minus t would yield s intersection with t complement, where t complement equals x minus t. Two sets S1 and S2 are said to be disjoint. If S1 and its intersection with S2, then you have an empty list, which is what we have seen, assuming there is no elements there. But let's understand this. So you have S, then we have T as a subset of X. Then S minus T, according to the rule, S minus T would equal to S intersection with T complement, where T complement equals X minus T. Yeah, of course. Yeah, okay, I think I got this. So we've got, say we've got 1, 2, and 3. That's for S. And for T, we've got 4, 5, and 6. And then for X, let's say we've got is a subset. So it's 4, 5, 6, and 8. Okay, so yeah, so we know T is a subset of X, is a proper subset of X, and then S minus T, so T complement would yield 1, 2, and 3, right? Yeah, so it's 1 and 2 and 3, where T complement is X minus T. So X minus T is 8. So we have 8. This is 8. So, and there's no intersection, so it's an empty list. Yeah, but what's that has to do with anything? Okay, so let's just try to get this logically without going through this example. I feel like it's a bit confusing because it's just using notations instead of using a real proper example with sets. So let's stick with the logical explanation of the notations. So this notation, okay, so similarly the intersection. So we've seen that the union should at least the results would have at least all the elements of one of the sets in the collection. Now, for the intersection, it's saying that x where x belongs to Si, that's fair enough. So for all I belong to M, so the intersection at least 1 for all I belongs to positive integers. For all I. Alright, let's see where this is leading us. I find it is a bit confusing here. Now, because you have at one point in time, saying is the set of all elements that are members of at least one of the SI. So all the elements of at least one of the SI. Yeah, because it's basically you're guaranteeing, in the union, you're guaranteeing at least one of the SIs are in the union. But in the intersection, you could have an empty list, and for all, it should be for any element. Yeah, furthermore, success S1 are said to be disjoint. So an intersection of S2 would yield an empty set. And for the intersection, you would have, oh, I think what all of this is doing is just giving us a definition of the unions and the intersection. I think it would have been a lot easier. So what are they saying is that if you have a set, if a set is a union of another set, then at least one of the sets is in the end result. So it's like at least one, be it assuming it's S1 is 1, 2, 3, and S2 is an empty set, then at least one is in the end result. And for the intersection, things are said to be a little different because for the intersection, you have to have a shared element in both sets. So so the element has to exist in all of the sets. I think that's what this means. Because, in this case, for the intersection not to be an empty set, you will have, in that case, it's going to be called a disjoint set, like we have here, S1 being 1 to 3 and S2 being 4, 5, 6. This would yield an empty set because they are disjoint. But if you have an intersection of, say, between S2 and S3, 4, 5, 6, and 4, 5, 6, and 8, S2 and S3, the intersection, now the intersection has to be the elements of all of the elements of uh, of the sets. And the elements should exist in both sets where I belongs to the positive integers. Got it, got it. So this is basically just giving us the definition of the union and intersection, and I think it would have been a lot easier if they opted for the another approach that we've seen in math. Maths is fun, Venn diagram. So I think this is what all this is saying. And then we come to De Morgan's formula, where you have, say, S1 union, or say, sorry, S1 union S2, all complements. Now, with De Morgan's law, or with De Morgan's formula, what this is saying is that it would go like S1 complement and then intersection S2 complement. You basically negate all of the elements within the sets. So you just like go and distribute all of the complements. As you can see here, the union would become an intersection, and then each of the elements would go to its complements. And then the intersection would be a union, and so on and so forth. There is a proof here that I really don't think we really have to go through it, but well, I really don't think we have to. It's necessary. And I think the book could have used a different approach. I mean, I understand that it gives us an indication as to what's really important. And the problem is, if we're going to use this book down the line, we will have to get acquainted to these terms here, like the union and the intersection, SI and positive and all this stuff. Well, I think we have a pretty good understanding. um, Rather technical results. It's in fact directly useful not only in mathematics but also many engineering fields such as digital electronics and so on and so forth. So what they're saying is, So let's try to go through the proof just to see what the hell is going on. So X belongs to the union of elements in Si and all complements. If and only if X is an element of some Si complement, hence if and only if X is not an element of some Si, hence if and only if X is not an element of the intersection Si, and therefore only if X belongs. Oh my god, what the hell? Whatever. Finally, S1 of the Sn is a collection of sets. We may form the ordered set of all n tuples. Okay. Cartesian product of Si. Is a collection of sets we may form the ordered set of all n tuples. Cartesian product. Probably the most common example of the Cartesian product is the plane real number square. So r multiplied by r. Each point x belongs to r square has coordinates x and y, where x, y belong to r. In order to facilitate the generalization to Rn, we will generally write equals x1 or x to the power of n, power of 1. Only the latter notation is used extensively in more advanced topics such as tensor analysis. There is usually no confusion between writing the components of a superscript and they being interpreted as exponents. Chapter 11. So the Cartesian product is basically, okay, it's A and B and C, B sets. Prove that A minus B intersection with C equals. So these are a set of exercises. I don't know, it's nice that it covers the notation, the weird notations, but I'm not sure that this is. I'm starting to doubt the book, to be honest. But well, let's keep going. What do we do next? So we've seen the sets here. So we've got this. Where is it? We've got this set of summary here. So this is De Morgan's law, where A union B to complement, then A complement intersection with B complement, and the same goes for the intersection, becomes a union. Number of elements in a set. What does this mean? The number of elements in a set A union B would equal the number of elements in A plus the number of elements in B. So you're basically trying to say the end results. Why don't you just add the number of elements? Yeah, but you have some duplicates, and then minus an intersection with B. So A, B, C minus A intersection with B, B intersection with C, and A intersection with C, and A intersection with B intersection with C. It's pretty weird stuff. And why are you doing this? Oh, okay, so we've got some examples here. So these examples prove what we're saying, prove the formulas up here. All right. So let A be 0, 1, 2, 3, 4, 5, and B be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5. This is a superset of this. 2, 3, 4. No, there is no 0 here, so this is not a subset superset relationship. And then we've got 4, 5, 6, and 7, and 8. So A union B union C union D. A union B, so you would union all of these and remove all the duplicates. So we have 0, 1, 2, 3, 4, 5, 6, and then we have 7 and 8. An intersection of B, by intersecting with B, we will have 1, 2, 3, 4, 5. Where is it? 1, 2, 3, 4, 5. And B intersecting with C, B intersecting with C. B and C. We have 2, 3, 4, 5, 6. And C with D, we have 4, 5, 6, 7. A with C, we have 2, 3, 4, 5. And A with D, we have 4 and 5. B with D, we have 4, 5, 6. Okay. A intersection with B intersection with C. A intersection with B intersection with C. So A intersection with B, we have 1, 2, 3, 4, 5. Intersection with C, we have 2, 3, 4, 5. 2, 3, 4, 5. Okay, that's now the number of elements. The number of elements of A is 6. The number of elements of B is also 6. The number of elements of C is also 6. The number of elements of D is 5. D is 5. Now the number of elements A union B union C union D. Now we don't have to go through all of this, but it's 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so what's the deal with the formula here? Number of elements. So we could go like the number of elements in A, that's 6, plus the number of elements in B. Yeah, so it goes through all of this. Damn. Okay. So why do I have to do the formula when I can just answer this and calculate the end result? I don't know, it just feels like the formula requires more effort, especially in cases like this. It would have been easier. A union B, then union C, then union D. I don't know. Maybe if we have like huge, terrible, like massively huge sets, it would make sense. Yeah, I think that would make like if you could, if we could have this programmed in a way that just detects what's common between the different elements. Then, yeah. L H S R H S. Left hand side, right hand side. Yeah, so the formula here is basically saying the number of elements of A plus the number of elements of C. But this is for the union. I'm not really sure if the intersection would apply here, because number of elements in A cross intersection with B intersection with C. There's no definition here. Number of unions. That's what he has introduced. But what about the intersection? Hmm. Just went on and listed all the possibilities. A union B equals an empty set. Therefore, either A equals an empty set. Oh, yeah, of course. A union B is an empty set. That means A is an empty set and B is an empty set. A minus B equals an empty set. Means A equals B is a subset of B. A minus B equals A intersection with B complement. Minus B is a subset of B. A minus B intersection with A minus C. A minus B union A minus C intersection with B minus A intersection with C. Cartesian product of all ordered pairs. Hmm. So I think we have some work to do with the sets because I understand we've got this basic understanding, but apparently as the lists or the sets grow real huge, you'll have to go with the mathematical formulas, and one has to memorize those or at least have an understanding of how those work. So I think we need to do more exercises on this. Apparently, it's like super important. I mean, assuming when you apply this to machine learning, assuming you have a set of um, some elements of given characteristics, and those characteristics you want to detect you want to cluster them based on the things they share. So you'll have to go like unions and calculate the number of elements in this and calculate the number of elements in that, and then get the unions, get the crap. Oh boy. Right, right. When you have like subtraction, and then you have like the Cartesian product, and then you have like this is a really important summary. So let's keep this here for now, and let's try to go back to set theory. What is this formulas? Let's see what this is all about. Hmm, not bad. It's like you've got a whole list of formulas here. So maths is fun. This is the Fourier, which is not bad. Let's go back to main site. There we go. So maths is fun. Sets and Venn diagrams. Now I'm not sure where should I go from here. Overview. See the quick results. Quiz results. Sets and Venn diagram. Just access to the formulas. Okay. Combinations and permutations. Quiz results. Alright, so we're through with the sets, we've done the exercises. Sets index. Let's see what this is all about. I've seen this, but I can't remember what. Yeah, so this is the this is the index. Okay. Set builder notation, set of all points, locus, common number sets, real number properties, set symbols, power set maker. It's a function, set theory index. Okay, so let's see what's this interval. What's this topic is all about. Intervals, all the numbers between two given numbers. All the numbers between 1 and 6 is an interval. Okay. All the numbers, yes. All the real numbers that lie between two values. The interval 2 to 4 includes numbers such as a lot more. This is nice. Crop this here. You know what? Let me put it directly in the drive. There we are. Back to the. This is an interval. So an interval is just basically like a bin in statistics, including the numbers at each end. Maybe yes, maybe no. We need to say. Boxes up to 20 kilograms in mass are allowed. Boxes exactly 20 kilograms. Will that be allowed? Up to 20, yes, it is. Well, usually that's what I understand. Saying that it isn't really clear. Let's see how to be precise about this in each of these popular methods. Inequalities, the number, line, interval notation. The inequalities is greater than or equal, less than or equal. Fair enough, less than or equal 20, then 20 is included. The interval notation, we just write the beginning and ending numbers of the interval and use square brackets when we want to include, okay, when we don't. This is a new information for me. That's a good one. So include 0, not 0, not 20, not 20. So not 5, but include 12. With the number line, we draw a thick line to show the values we are including. And a filled circle. Oh man, this is pretty nice. This is what's different. I mean, the book is like way off with the mathematical notations. This is why this is better. Now we understand the empty circle here. The filled one includes the number it's pointing at, and the other one doesn't. So all three together. Oh, it's a pretty nice summary. There's a handy table. Yeah, like this. Let's see if this actually is printed in the document. Maybe not the best one. It's not included. Let's see if we try to do this. Yeah, it's a handy table. So I think this is a topic we shouldn't be spending a lot of time on. Unions and intersections. We just saw how to join two sets using union using symbol U. As also which means has to be in both. Think where do they overlap? The intersection symbol is an upside down U. Mm-hmm. goes up to 6, including 6. Second interval goes up. So this is the union here. This is the intersection. Mm. An interval is all the numbers between two given numbers, showing if the beginning and end are included is important. There are three main ways to show intervals: inequalities, a number line, and interval notation. I think it's time to hit the exercises. Yeah, is it mathematically amazing? Yeah, if it's properly explained, yes, it is amazing, but it's using the weird notations that we've seen in the previous book. It's really crazy, man. Okay, great, great, great. So let's do let's go with the exercises now. Okay, write the inequality for less than or equal x less than 9 in an interval notation. So this is a squarish, and that's definitely it. Which of the following number lines illustrated the inequality? Negative 5 is less than x. No, it's negative less than x, but less than or equal. It's definitely a C, because we don't have the equality sign here, so it's not included. Negative 5 is not included. While a 4 is greater than or equal 6 and greater than or equal negative 3. So 4 is included, but the 3 is not. It's actually this. It's right. The right way around. Yeah, so this is the correct way. Right, what inequality is defined in interval notation by um, negative infinity to 2. So x is less than or equal to is less than or equal to negative 2. Yeah, and x are greater than or equal to 3. That's the union, so that's the OR. What inequality is defined in interval notation by, so this means that it's less than or equal 3 and greater or equal 1. Yeah, this is it. The interval shows the interval shown in the number line can be expressed as which inequality. So we have now this is x is greater than or equal negative 5, but less than 4. Which of the following describes in interval notations? In interval notation, the inequality shown in the diagram. So in this case, x is less than negative 2, x is less than negative 2, union x is greater than 6. Yeah, so in this case it's infinity, so not including, so it's minus infinity union 6 to infinity. This could be, no, it's not an intersection, it's actually a union. Which of the following interval notations is the same? In this case it's an intersection, that's for sure. Then we have, it's not so minus 1, it's not minus, okay, so it's minus infinity to 5 union minus 1 and positive. No, it's actually an intersection with positive. 5 is not included, so these both are invalid, so this is it. Which of the following describes in interval notation the inequality shown in the diagram? So we have -7 to infinity, not included, and then we have intersection. It's actually an intersection. -2 is included. Which of the following? This is a union. 8 is not included, and 3 is actually included. So it's -3 union 8 to positive. Yep, 100%. Awesome. So we're through this intervals. We've done this. We're good. What else? Interval set builder notation. It should be only notations and all. Set is a collection of things, such that. Oh, okay. This is really interesting. This is what we've been looking for. The notations that the book has been driving us crazy with. I think if we go through this, we will have a really good understanding of what the book is just trying to say. Let me stop here for now and continue later.